Hello everyone, my name is Vincent and welcome back again to my tutorial, step-by-step tutorial. And today we are going to talk about IP problem. So we are going to talk about the marriage problem and namesake problem for the next few lessons, okay? So for now, let's start with a little bit of definition about what integer programming is and how is it different from linear programming. Well, in terms of the methodology, integer programming is a little bit more advanced because that once you have done the linear programming, let's say that this is the optimal LP solution, which is a linear programming. Well, the thing is that for the integer programming, your solution needs to be in the blocks. So it couldn't be a continuous numbers, that it couldn't allow decimal points. So it needs to be in a block like 3 or 4 or 5. But it still needs to be within in boundaries. So the first thing that we can do here is that we need to restrict the solution. So if you see the plus here, it's basically the combinations of the possible integers within the decision boundaries, which is the shaded areas. Okay? And by the end of the day, what we can do is that we can do branch and bound problems, meaning that given the optimal LP solution, we can see what is the upper bound, which is marked by the red line at the 4 here, and the lower bound, the red mark on the 3 here. Okay, and this will create subproblem A and subproblem B, these definitions, and maybe we can do it in a smaller scale, and then it keeps going on until it finds a root into a smaller problems. And well, and by the end of the day, you can see that which one is the closest to the optimal LP solution. So it will test out these 2, 3, 1, 3, 1, 3, 2, 4, 0, 4, 1. Well, that is my understanding about what's happening. But of course, I honestly think there are a little bit of variations out there about what branch and bound possibly is. It could be something that's more complex than this, but in the hindsight, from what I've learned, it means something like this, like keep going on iteratively until at the end that you will find what is the optimum just by looking at branch, upper bound and lower bound from the optimal LP solution. Okay, so you test them out. But I would like to highlight the fact that for the integer programming problem, the optimum variable solution will always be lower. Why? It's because that we are restricting the possibilities of the decision boundaries. Instead of the whole set of areas, we're limiting those to only the plus areas. So we are limiting, we couldn't have this optimal dot anymore, but we need to settle with something that is less than that, or even more less than the optimum value, which is, well, more x or more y, something like that, or less x, more y, more y, less x. So those that are out a little bit not optimal solution. So that is why that integer programming is actually making the optimum solutions less, because you're limiting the boundaries. Okay? Right, so let us talk about the marriage problem, which is one of the nice LP program and quite simple to explain. Okay? So let's say that you have Disney characters, Minnie Mouse, Daisy Duck, they're looking for couples. So you arrange a meetups with the guys and the girls, and they would like to choose the best couples to minimize total disutility. So disutility, if there's a mismatch of the couple, so let's say Minnie Mouse is matched with Donald Duck, then of course there will be some contention going on because they are not the same species. For example, they are duck and mouse. So that is the disutility. So how are you going to minimize these conflicts? Right? So this is a disutility score. So if Daisy Duck is with the bees, Daisy Duck will feel very, very sad because he doesn't want to be paired with the bees. So you see here 4. But Daisy Duck with Donald has sort of okay kind of like disutility. So like maybe we can pair Daisy Duck with Donald because like, they are happier than Daisy Duck with the bees. So that's how you read this table. And then keep going on Mickey, Popeye, Minnie Mouse, okay? So Again, we formulate it with the decision variable, objective function, and constraint. So whether male I should be paired with female j, and objective function is to minimize the disutility or the dissatisfactions. So it will be the sums of xij and dij. The difference here, if you notice, is this xij doesn't mention about the quantity, but it mentioned about the possibilities whether it should be a pair or not pair. Is male I paired with the female j or not? So it's only 1 or 0. 1 means it's true, they are a pair. Donald Duck, X Donald Duck, and Daisy is 1, so means like Donald Duck and Daisy is a pair. Okay, if there's a pair, then there's a disutility, possible disutility coming up. So you need to multiply it by the disutility. So this is how it means. Okay, it will be very clear once we get to the solution. Okay, and after that we have constraints. So male is paired to one and only female, and female is paired to one and only male. So of course, xij for all I for Donald Duck, the Donald Duck mini, Donald Duck olive oil, it can only be 1. So Donald Duck can only be paired to one female. And same thing goes around with the Donald Duck Minnie Mouse being paired to one male. Okay, so for this one more than equals to 1 here, it has to be equals to 1. And in the constraint, it can be 0 or 1. You couldn't be like 0.5. You could be like, oh, I pair up with you, but I don't pair up with you at the same time. So you couldn't do that. So only 0 or 1, which is integer. Okay, binary to be precise. All right. So now let's go through the Excel sheet. So for the Excel sheet, well, we have the disutility score. So this is a template that I already created. Okay, and afterwards, then we will use the disutility scores to find the pairing. So the pairing will be like, well, 1 0 1 0 0, something like that. So Beast is a pair with Beauty, well, but not a pair with Daisy Duck, Minnie Mouse, and Olive Oil. So that's how you read. And then the pairing is basically just the sum of these numbers. So the pairing of this needs to be 1. So we can do this again with the male and female. So the male is the rows lattice, and the female is the column lattice. Okay, so so we can do something like this. So one possible answers would be possibly this is the 1. So 0 0 1 0 0 0 0 1. So this is possibly what we want. We want everyone to be paired by 1, and we want everyone to be paired by 1. So this is one possible answers. Or possible to be like this also. So there you go. Or once this is also possible. So donor is paired with Beauty. But let's say we don't know anything yet, so we delete all of this. Okay. And total disutility basically is just sum product. So again, sum product of this, the Beauty female, comma, the array 2 is the disutility score. So this is the 1. So if I put 1 0 0 0 here, or maybe sorry, because it's 0 doesn't cannot see, but let's say this is the 1. Okay, so you see the total disutility 2, because Donald Duck, the 1 and 2. So 1 times 2 becomes 2. So there is a disutility that you collected now, which is 2. Alright. So, well, let's replicate this formula with the others. So we are happy. Okay, and by the end of the day, we want to minimize the sum of the disutility of each of the female. So count is 0. The constraint is we only have, well, integer and then pair is 1 and only 1. So yeah, we can do that. So how we're going to formulate this is we can use solver. So I already have it, so but let me delete this so that we can start from the beginning, easier to see. So what is the objective? Objective is in order to minimize the disutility. So G10, okay, and then by changing the variable what cells. So this is the variable that I want to change. Okay, this will be a number. but I will add on the constraints that each can only be paired to 1, so equals to 1. Okay, and same thing also with this pairing, so this will be equals to 1. Okay, and finally this needs to be an integer. So there you go, and click OK, then you will have 3 of these, right? Use simplex LP, make our constraint negative, and then you should run it, so this should succeed. There you go. So I have the solutions. So notice here that the only problem with the integer programming is that you do not have the sensitivity analysis. Because sensitivity analysis is mostly done at the level of linear programming. But for the integer programming, because you are limiting your solutions, it's actually not that feasible for you to find the sensitivity analysis. So therefore, Solver does not include because it's computationally harder. Alright, so yeah, just one note for you to see. And if you click OK, then you find a possible pairing. So Beast is good to be with Beauty, Donald is good with Daisy Duck, Mickey is good with Minnie Mouse, Popeye is good with Olive Oil. And then if you see the total distributed here, then you'll find that the total is 3. But Daisy Duck will have utility distributed of 1, Olive Oil will have distributed of 2. So that is how you read the marriage problems and how you solve it. So what can be applied? Well, maybe you can apply it for Tinder, or maybe your pairing journey. You can see like how matchful are you with the others, considering that you care about your friends, with your clique of the groups. Those if you're a girl, then your gang of drinking at the clubs. Then you pair up with boys, that kind of things. So this is good to use if you have that kind of problem. But definitely in terms of business assignment problem, this is very good. For example, you have several machines type A, type B, type C, type D. They can produce 3 types of products. Then you can actually like compare them. So machine A for type of product B and machine B type of product A. So those that can produce in a more efficient way. So that is something that you can do with it. Alright. So moving on. Then that's all about the marriage problem. Then moving on, you can do many kinds of solutions with this, and we are trying to optimize another knapsack problem with Goodreads, or maximizing or optimizing our reading problems. Okay, with that, I would like to close an end to this tutorial, and see you.